In 1987, a team of Soviet and French scientists published a paper that changed how we understand the planet we live on. They had spent years drilling into the Antarctic ice sheet at a remote station called Vostok, extracting cores of compressed ice from depths that no one had reached before. The ice at the bottom of their drill had fallen as snow 420,000 years ago, before modern humans existed, before Neanderthals dominated Europe, in a world that looked almost nothing like the one we live in now. When they analysed the chemical composition of that ice, layer by layer, year by year, back through 420,000 years, they found a pattern so precise, so regular, so unmistakably periodic that when they plotted it on a graph, it looked less like a natural record and more like something engineered. 4 complete cycles visible in the data, 4 times, over 400,000 years the same sequence had played out. The planet had cooled slowly and gradually over roughly 90,000 years, building vast ice sheets that covered enormous portions of the northern hemisphere. And then, at the end of each cycle, the ice had collapsed. Rapidly, catastrophically by geological standards. Within a few thousand years, the world had lurched from deep glaciation to a warm interglacial, the ice retreating, sea levels rising, vegetation zones shifting dramatically. And then the cycle had begun again, 100,000 years, like clockwork, not perfectly, not with the precision of an atomic clock, but close enough that the deviation from the pattern is smaller than the pattern itself. The planet resets approximately every 100,000 years. The ice comes, the ice goes, the world changes. And then the process begins again. The Vostok paper was not the first evidence for this cycle. The pattern had been theorized decades earlier, and earlier cruder evidence had pointed toward it. But the Vostok core was the first record long enough, and detailed enough, and chemically precise enough to make the pattern undeniable. 4 complete cycles, temperature going up and down in near-perfect regularity, carbon dioxide tracking the temperature with a correlation so tight that the 2 signals are almost superimposed, a planetary heartbeat preserved in ice, beating at a frequency of 1 pulse every 100 millennia. Here is what haunts me about this. The ice is telling us something about the Earth system that we do not fully understand. We know the pattern exists, we know the approximate mechanism, but the specific details of why the planet behaves this way, why the rhythm is what it is rather than some other rhythm, why the ice builds slowly and collapses fast, why the pattern shifted dramatically about 1 million years ago, those questions are still genuinely open, still being debated in journals and at conferences by the best climate scientists alive. The planetary heartbeat is real. The complete explanation for it is not yet in our possession. That gap between pattern and explanation is what makes this story so extraordinary. Because what we do know is remarkable enough. What we do not know is an invitation. In 1879, a Serbian boy was born in the village of Dalj, in what is now Croatia, to a family of farmers. His name was Milutin Milankovitch. He was a mathematician by training and by inclination, and he eventually became a professor at the University of Belgrade, where he was teaching in the summer of 1914 when the assassination of Archduke Franz Ferdinand happened nearby and the First World War began. Milankovitch was in Vienna when war was declared. As a Serbian citizen in the Austro-Hungarian Empire, he was immediately considered an enemy. He was arrested and interned. He might have spent the war in a prison camp. Instead, through the intervention of a friend and colleague, he was allowed to spend his interment in Budapest in relative comfort, with access to the library of the Hungarian Academy of Sciences. He had brought his mathematical notebooks with him, and in the library in Budapest, across 4 years of war while the world outside was destroying itself, Milankovitch worked on a problem he had been thinking about for years: the astronomical theory of ice ages. The idea that astronomical cycles might drive ice ages was not new. It had been proposed in various forms by others, most notably the Scottish geologist James Croll in the 1860s, but Croll's calculations were incomplete and his theory had problems. Milankovitch approached the problem with the systematic rigour of a mathematician. He wanted to calculate precisely how the amount of solar radiation reaching the Earth's surface at different latitudes varied over time as a function of the astronomical cycles that affect the Earth's orbit and orientation. He wanted numbers, exact numbers, covering hundreds of thousands of years. It took him decades. He worked on it in Budapest during the war. He continued after the war back in Belgrade. He published increasingly refined calculations through the 1920s and into the 1930s. The final comprehensive version of his work was published in 1941 in German in a book called Kanon der Erdbestrahlung und seine Anwendung auf das Eiszeitenproblem, which translates roughly as Canon of Insolation and the Ice Age Problem. The book was remarkable, a monument of mathematical astronomy applied to a geological problem, and it was almost immediately overshadowed by the Second World War, and for decades afterward it was largely ignored by the scientific community, which was sceptical that astronomical cycles could explain the ice ages. The correlation between Milankovitch's calculated insolation curves and the actual record of ice ages seemed unconvincing to many researchers, partly because the geological record of ice ages was not yet well enough characterized to provide a robust test. It was only in the 1970s, and especially after the Vostok core data of the 1980s, that the Milankovitch theory was comprehensively vindicated. The deep-sea sediment cores and ice cores provided exactly the kind of detailed, continuous climate record that was needed to test the theory. And when the test was made, the astronomical signal was there. The frequencies of the Milankovitch cycles appeared in the climate record with statistical robustness. The theory that a Serbian mathematician had worked out by hand in a Budapest library during the First World War turned out to be, in its essential outlines, correct. Milankovitch died in 1958, old enough to see the beginnings of the modern era of paleoclimate research, but not old enough to see the Vostok vindication of his life's work. He knew he was right. He died not knowing if the world would eventually agree with him. It did. So what are the Milankovitch cycles? There are 3 of them, operating on different timescales, each one a different aspect of the Earth's orbital and rotational geometry, and each one affecting the amount and distribution of solar energy reaching the Earth's surface in a different way. The first cycle is eccentricity. This refers to how elliptical the Earth's orbit around the Sun is. An orbit can be perfectly circular, with the Sun at the exact centre, or it can be an ellipse, with the Sun at one focus of the ellipse. The Earth's orbit is currently slightly elliptical. At its closest approach to the Sun, called perihelion, the Earth is about 147 million kilometres from the Sun. At its farthest point, called aphelion, it is about 152 million kilometres away. The difference is about 3%. This eccentricity is not constant. It varies over time due to the gravitational influence of the other planets, particularly Jupiter and Saturn. The eccentricity cycles between nearly circular and slightly more elliptical over timescales of roughly 100,000 years and also 400,000 years. When the orbit is more elliptical, the difference in solar energy received between perihelion and aphelion is larger. When the orbit is more circular, the difference is smaller. But here is the crucial thing to understand about eccentricity. The total annual solar energy received by the Earth does not change very much with eccentricity. What changes is the seasonal distribution of that energy. More eccentricity means more contrast between the season when Earth is closest to the Sun and the season when it is farthest. Less eccentricity means a more even distribution of solar energy across the year. And the global average change in solar energy from maximum eccentricity to minimum eccentricity is small, approximately 1/10%. This is important, because the 100,000-year cycle, the dominant beat of the ice ages over the past 800,000 years, corresponds to the eccentricity cycle, and the eccentricity cycle produces the smallest change in total solar energy of the three Milankovitch cycles. Somehow the weakest astronomical forcing produces the strongest climate signal. This is what climate scientists call the 100,000-year problem, and it is one of the most important unresolved questions in paleoclimatology. The second cycle is obliquity, also called axial tilt. The Earth's rotation axis is not perpendicular to its orbital plane, it is tilted. Currently the tilt is approximately 23.5 degrees. This tilt is what causes the seasons. When the northern hemisphere is tilted toward the Sun, it receives more direct solar radiation and has summer. When it is tilted away, it has winter. The obliquity of the Earth changes over time, cycling between approximately 22.1 degrees and 24.5 degrees, with a period of approximately 41,000 years. When the tilt is larger, the seasons are more extreme. Higher tilt means hotter summers and colder winters in both hemispheres. When the tilt is smaller, seasons are more moderate. Smaller tilt means cooler summers and milder winters. For understanding ice ages, the summer temperature at high latitudes matters enormously. Ice sheets do not grow because winters are cold enough to produce snow. Winters at high latitudes are already cold enough for that. Ice sheets grow when summers are cool enough that the winter snow does not completely melt. The ice accumulates year by year, building the great ice sheets. So smaller axial tilt, which means cooler summers at high latitudes, favours ice sheet growth. The obliquity cycle has a period of 41,000 years, and the climate record shows that before approximately 1 million years ago, the dominant period of ice age cycles was indeed 41,000 years. The Earth's ice ages marched to the obliquity beat. Then something changed. The dominant period shifted to 100,000 years. This shift is called the mid-Pleistocene transition, and it is one of the great mysteries of paleoclimatology. More on that shortly. The third cycle is precession. This is the wobble of the Earth's rotation axis. Think of the way a spinning top wobbles as it slows down. The Earth's axis similarly wobbles, tracing a circle in space over approximately 26,000 years. This wobble means that the season during which the Earth is closest to the Sun changes over time. Currently, Earth is closest to the Sun in January during Northern Hemisphere winter. This moderates the Northern Hemisphere season slightly, making winters a bit warmer than they would otherwise be, and summers a bit cooler. But 12,000 years ago, precession had the Earth closest to the Sun in July, during Northern Hemisphere summer. This made Northern Hemisphere summers warmer and winters cooler. In another 12,000 years, the configuration will be back to perihelion in Northern Hemisphere summer. Precession interacts with eccentricity to produce the actual seasonal forcing at any given time and place. When eccentricity is high and perihelion coincides with Northern Hemisphere summer, the difference from perihelion to aphelion is more extreme, and the summers are particularly warm. When eccentricity is high and perihelion coincides with Northern Hemisphere winter, this summer warming is reduced. The three cycles do not operate independently. They interact. They reinforce each other at some times and partially cancel each other at others. The actual insolation, the solar energy reaching any given latitude in any given season, is the result of all three cycles operating simultaneously. And the climate response to insolation changes is further modified by feedbacks within the Earth system itself. Feedbacks that are, in some ways, as important as the astronomical forcing. The most important feedback is the ice-albedo feedback. Albedo is the reflectivity of a surface. Fresh snow has very high albedo, reflecting about 80 to 90% of incoming solar radiation back into space. Open ocean has very low albedo, absorbing most incoming solar radiation and converting it to heat. Ice-covered land has high albedo like snow. Vegetated land has moderate albedo. When an ice sheet grows, it replaces low albedo land or ocean with high albedo ice. The planet reflects more solar energy. The planet cools further. More ice grows. The cooling amplifies itself. This is positive feedback, meaning the initial change is amplified by the response to it. A small cooling causes more ice growth, which causes more reflection, which causes more cooling. When an ice sheet retreats, the opposite happens. The high albedo ice is replaced by darker land or ocean. The planet absorbs more solar energy. Temperatures rise, more ice melts. The warming amplifies itself. This ice-albedo feedback is partly responsible for the asymmetry of the glacial cycle. The sawtooth pattern, the slow build-up and rapid collapse. During the build-up phase, the orbital forcing is gradually driving the planet toward cooler conditions. The ice expands slowly, incrementally, each year's accumulation slightly exceeding each year's melt. The ice sheets grow over tens of thousands of years, gradually extending their reach southward, gradually increasing the planet's albedo, gradually cooling the climate further. But the collapse is different. At glacial maximum, when the ice sheets are at their largest extent, the ice has modified its own environment in ways that make it increasingly vulnerable. The large ice sheets compress and depress the crust beneath them, lowering the surface elevation of the ice over time. The large ice sheets increase the albedo so dramatically that the planet's heat budget is profoundly altered. And when the orbital configuration begins to favour warming, the positive feedback of the ice-albedo mechanism begins to run in reverse. The initial warming reduces ice extent. Reduced ice extent reduces albedo. Reduced albedo means more solar absorption. More solar absorption means more warming. More warming means more ice loss. The collapse accelerates. What took 90,000 years to build can be largely demolished in 10,000 years. The ice sheets are not just melting, they are catastrophically failing, driven by the same feedback mechanism that built them, now running in reverse. The second crucial feedback is carbon dioxide. The Vostok ice core data showed something that initially surprised researchers. The carbon dioxide concentration in the ancient atmosphere, preserved in bubbles in the ice, tracked the temperature signal almost perfectly. When temperatures were low during glacials, carbon dioxide was low, approximately 180 parts per million. When temperatures were high during interglacials, carbon dioxide was high, approximately 280 parts per million. The two signals moved together through 4 complete cycles. This raised an immediate question. Was the carbon dioxide driving the temperature, or was the temperature driving the carbon dioxide? The answer, as best as current science can determine, is that the temperature change leads. The carbon dioxide change slightly. The astronomical forcing initiates a small warming. That warming changes ocean circulation and temperature, and as the deep ocean warms, it releases carbon dioxide that had been dissolved in the cold water. The released carbon dioxide amplifies the warming through its greenhouse effect. The amplification is substantial. The astronomical forcing alone is not sufficient to drive the full magnitude of the glacial-interglacial temperature change. The carbon dioxide feedback provides a significant fraction of the total signal. In the other direction, when the astronomical forcing begins to drive cooling, the ocean eventually cools enough to absorb more carbon dioxide from the atmosphere. The reduced carbon dioxide reduces the greenhouse effect, amplifying the cooling. The feedback runs in both directions. This matters for understanding the modern climate. The carbon dioxide concentrations that drove warm interglacials in the past were approximately 280 parts per million. The current atmospheric carbon dioxide concentration is over 420 parts per million, higher than at any time in the past 800,000 years of ice core records, and almost certainly higher than at any time in the past 3 million years. The greenhouse forcing associated with this concentration is outside the range of natural variation that drove the Milankovitch cycles. We are running an experiment with the same lever at a magnitude unprecedented in human evolutionary history, but that is a thought for later. For now, let us go deeper into the cycle itself, into what the planet actually looks like during a glacial maximum, into what it means to live on an Earth that has completed its slow build-up of ice and is sitting at the cold, compressed, reflective extreme of its 100,000-year heartbeat. The glacial maximum looks nothing like the world we know. This is not a modest statement. The differences between a glaciated Earth and an interglacial Earth are so profound, so comprehensive, so visually and ecologically dramatic that the two states of the same planet might as well be different planets. The most recent glacial maximum, called the last glacial maximum or LGM, reached its peak approximately 26,000 years ago and persisted for several thousand years before the deglaciation began. The last time the planet was in a mode comparable to the previous LGM before that was approximately 140,000 years ago in the glacial stage preceding our current interglacial. At the last glacial maximum, the Laurentide ice sheet covered essentially all of Canada and extended deep into the northern United States. Chicago, which today sits at 42 degrees north latitude, was under more than a kilometre of ice. The ice extended south into Ohio, Indiana, and Illinois. The ice sheet over North America was so massive that its weight had depressed the crust beneath it by hundreds of meters. The bedrock of Hudson Bay, which was under the thickest part of the ice sheet, was pressed down far enough that when the ice melted, the land rebounded upward, and that rebound is still happening today. Parts of Scandinavia and Canada are still rising, measurably, thousands of years after the ice disappeared, the crust slowly recovering from the weight of the load it carried for tens of thousands of years. The Fennoscandian ice sheet covered essentially all of Scandinavia, the British Isles, and much of northern Russia. Ice extended across the North Sea. Britain was connected to the European continent not by a land bridge precisely, but by a landscape of ice and frozen tundra that was not navigable as ocean. The Irish Sea was dry land. The North Sea was a frozen lowland. Sea levels were approximately 120 metres lower than today. 120 metres. That number sounds abstract. Think of it concretely. Every coastline in the world extended further than it does now. The continental shelves, the shallow water areas surrounding the continents, were in many places dry land. The Gulf of Mexico and the Atlantic coast of North America were 50 to 200 kilometres further out than today. The coasts of Australia extended to include what is now the shallow Sahul Shelf. The islands of Southeast Asia were connected to the Asian mainland in a large landmass called Sundaland. Japan and Korea were connected to China. Alaska and Siberia were connected by the Bering Land Bridge, a broad plain of tundra and grassland that was not merely a narrow strip of land but a subcontinent in its own right. The Amazon basin, which today receives enormous rainfall from the moist Atlantic trade winds, was significantly drier. The great tropical forests were reduced in extent, contracting into refugia in wetter pockets, while grasslands expanded. The Sahara Desert was larger and drier than it is today. The Mediterranean was smaller as coastal land was exposed. The pattern globally was of drier, cooler conditions in most of the tropics and subtropics, with the dramatic ice sheets confined to the highest latitudes, but their climatic influence felt worldwide. The atmosphere itself was different. Dust concentrations in the glacial atmosphere were many times higher than in interglacials. The cold, dry, windy conditions of the glacial world produced enormous amounts of wind-blown dust, called loess, which accumulated in deep deposits across Central Asia, across the American Midwest and across Europe. The lowest deposits of northern China, which can be tens of meters thick, are a direct record of the dusty glacial atmosphere, each layer of loess representing a period of glacial conditions, and each layer of soil forming on top of the loess representing a warmer, wetter interglacial or interstadial period. The global average temperature was approximately 4 to 7 degrees Celsius cooler than today. That does not sound dramatic, but the global average conceals enormous regional variation. The high-latitude northern hemisphere, where the ice sheets were, was dramatically colder. Greenland was approximately 20 degrees Celsius colder than today. The tropical oceans, which modulate global heat distribution, were only a few degrees cooler, but the modest cooling had large consequences for the atmospheric circulation patterns that deliver rainfall to the tropical continents, and the biological world was correspondingly different. The communities of organisms that lived in each region were entirely different from the communities that live there today. Not entirely absent in most places, but fundamentally reorganized. The species were the same species that had evolved over the preceding millions of years, but the specific combinations, the specific assemblages, the specific communities of organisms living together in a particular place were unlike anything that exists today because the environment that hosted them no longer exists. The megafauna of the glacial world, the woolly mammoths and woolly rhinoceroses and cave bears and giant ground sloths and cave lions and dire wolves, inhabited a landscape that is gone. The mammoth steppe, as it is called, The vast cold grassland that stretched from Spain across Eurasia to Siberia and across the Bering Land Bridge into North America no longer exists anywhere on Earth. It was replaced, as the ice retreated and the climate warmed, by the boreal forest in the north and by the modern temperate grasslands further south. The specific ecosystem in which the megafauna had evolved over hundreds of thousands of years was dismantled by the climate transition at the end of the last glacial, and the megafauna went with it. This is the world that the Milankovitch cycles create and destroy, not gently, not gradually in a way that gives organisms comfortable time to adjust. By the standards of geological time, rapidly. The termination of a glaciation, the transition from glacial maximum to interglacial, happens in a few thousand years. A few thousand years during which the ice retreats, sea levels rise, the great biomes shift their ranges, and the organisms that are unable to track the shifting conditions fast enough go extinct. If you are listening to this tonight, settling in, letting the story unfold, this is exactly the kind of story these videos are made for. If you find value in this kind of deep, carefully researched content, please subscribe and leave a like. It genuinely helps. And leave a comment telling me where in the world you are and what time it is. The geography of who listens to these never stops being fascinating. The sea level story deserves a moment of specific attention because it connects the astronomical forcing to one of the most concrete possible consequences of the glacial cycle. At the last glacial maximum, sea levels were approximately 120 meters below their current position. That water was in the ice sheets. As the ice melted during the last termination, that water returned to the ocean. During the most intense phases of deglaciation, sea levels rose at rates approaching 4 centimeters per year during meltwater pulses. Communities living near shorelines experienced the sea advancing within a single lifetime. The continental shelves that had been home to some of the densest prehistoric populations were inundated. Their settlements are now on the sea floor. The physics that drove that coastal flooding, ice melting and thermal expansion of warming water, is the same physics operating today, at a slower rate driven by a different forcing, but along the same causal chain. The 100,000-year cycle is not abstract. It moved coastlines by over 100 meters, repeatedly, and the memory of that movement is preserved in the myths of 100 cultures and in the sediment of every drowned continental shelf. Now let us talk about the problem that has kept climate scientists up at night for decades, the 100,000-year problem. The eccentricity cycle, the cycle with a period of approximately 100,000 years, produces the weakest change in annual average solar energy of the 3 Milankovitch cycles. The change in total annual insolation from minimum to maximum eccentricity is approximately 1/10 of 1%. The obliquity cycle produces a much larger change in the seasonal and latitudinal distribution of solar energy. The precession cycle produces large changes in the seasonal timing of perihelion. Yet the dominant frequency of Ice Age cycles over the past 800,000 years is approximately 100,000 years. The signal corresponding to eccentricity is larger in the climate record than the signal corresponding to obliquity. The weakest forcing produces the strongest response. This is genuinely puzzling. It is not immediately obvious from any simple consideration of the physics why the Earth's climate should respond most strongly to the weakest astronomical forcing. Several explanations have been proposed, and the debate is not fully resolved. One possibility is that the 100,000-year cycle is not actually a direct response to eccentricity forcing, but rather an emergent property of the nonlinear dynamics of the ice sheet system itself. Ice sheets have their own internal dynamics. They grow and reach a critical size at which they become unstable and then collapse. The time required to build up to that critical size, given the typical rates of ice accumulation and the typical variations in orbital forcing, might simply be approximately 100,000 years. In this view, the 100,000-year cycle is set by the internal physics of ice sheets rather than being directly driven by the eccentricity cycle. Another possibility involves the interaction of the eccentricity cycle with the 400,000-year eccentricity cycle. There is a longer eccentricity cycle with a period of approximately 400,000 years, and some researchers have argued that the 100,000-year oscillation is an interaction product, a resonance, between this longer cycle and the shorter ones. A third possibility involves carbon dioxide. If the carbon dioxide feedback is strong enough and has a natural oscillation timescale of approximately 100,000 years due to the specific dynamics of the ocean carbon cycle, then the 100,000-year climate cycle might be as much a product of ocean carbon dynamics as of direct astronomical forcing. The honest answer is that no single explanation has been fully accepted by the community. The 100,000-year problem remains genuinely open. The pattern is real, the ice cores prove it, but the complete quantitative explanation for why the pattern has that specific period rather than some other period is still being worked out, and then there is the related mystery of the mid-Pleistocene transition. Before approximately 1 million years ago, the Ice Age cycles followed a 41,000-year period, corresponding to the obliquity cycle. This is exactly what you would predict from basic Milankovitch theory. The obliquity cycle produces the largest seasonal forcing changes, so it makes sense that the climate responds to it. Before the mid-Pleistocene transition, the climate record shows regular 41,000-year oscillations, smaller in amplitude than the later 100,000-year cycles, somewhat more symmetric in their shape, without the strongly asymmetric sawtooth pattern of later glacial cycles. Then, between approximately 1.2 million and 700,000 years ago, the dominant period shifted. The 41,000-year cycles became less regular. Ice ages became more severe. The ice sheets became larger, and the dominant period shifted toward 100,000 years, the mid-Pleistocene transition. The astronomical forcing did not change at this time. The Milankovitch cycles were operating in the same way they always had. Whatever caused the shift in the climate's response to that forcing was internal to the Earth system rather than external. Several hypotheses have been proposed. One suggests that the progressive cooling of the deep ocean over the course of the Pleistocene, driven by the gradual growth of the Antarctic ice sheet over millions of years, eventually crossed a threshold that changed the dynamics of the Northern Hemisphere ice sheets. Another hypothesis involves the erosion of regolith, the loose soil and sediment from the Northern Hemisphere land surfaces. In the early Pleistocene, the ice sheets moved over thick regolith that provided a lubricated base, allowing the ice to slide easily and limiting how large the ice sheets could grow. As repeated glaciations eroded the regolith, the ice sheets came into contact with the underlying bedrock, which provided more resistance, allowing the ice to build to larger extents before collapsing. The regolith hypothesis is attractive because it provides a mechanism that would operate on the right time scale. Several million years of glacial erosion gradually removing the regolith, eventually crossing the threshold at which ice sheet dynamics changed. But this hypothesis, like the others, has not been fully accepted as the complete explanation. What the mid-Pleistocene transition tells us is that the relationship between astronomical forcing and climate response is not simple and linear. The Earth system is not a passive receiver of astronomical signals. It has its own internal dynamics, its own thresholds and feedbacks, its own history that affects how it responds to any given external forcing. The climate of 1 million years ago responded to the Milankovitch cycles differently than the climate of 100,000 years ago, not because the cycles changed, but because the Earth system itself had evolved over that time. This is a profound insight for understanding climate in general, including contemporary climate change. The Earth system is not a linear amplifier of external signals. It is a complex non-linear system with internal dynamics, thresholds, and state transitions. Understanding those dynamics is as important as understanding the external forcings. Let us go back to the ice cores, because the ice cores are the most extraordinary paleoclimate archive we have, and their story deserves more attention than it usually receives. The Vostok ice core, which provided the first comprehensive 420,000-year climate record, was eventually superseded by even deeper cores. The Epica Dome Sea Core, drilled by a European consortium and completed in 2004, extended the record back to approximately 800,000 years. 800,000 years of climate history, preserved in compressed ice at the East Antarctic plateau, accessible to the instruments of 21st century science. The Epica core shows 8 complete glacial cycles, each roughly 100,000 years in duration, each cycle following the same basic template: slow cooling over tens of thousands of years, interspersed with brief warm periods called interstadials, eventually reaching a glacial maximum and then a rapid termination, a transition to interglacial conditions in a few thousand years. 8 times, 8 complete repetitions of the same planetary drama. But the record also shows variation between cycles. Not all glacials are identical. Some are more severe than others. Some interglacials are warmer than others. The interglacial that occurred approximately 400,000 years ago in what geologists call marine isotope stage 11 was exceptionally long and warm, lasting significantly longer than typical interglacials. This stage is sometimes considered the closest analogue to the current Holocene interglacial because the orbital configuration at that time was similar to the current one. Stage 11 lasted about 30,000 years before the next glaciation began. This is relevant for thinking about the future of the current interglacial. The ice also preserves direct records of past atmospheric composition. Air bubbles are trapped in the ice as snow compresses to ice over hundreds of years. Those bubbles contain samples of the ancient atmosphere, preserved for hundreds of thousands of years. By extracting these bubbles and analyzing them, scientists can measure directly what the carbon dioxide concentration was in the atmosphere 200,000 years ago, or 400,000 years ago, or 800,000 years ago. The result is the remarkable correlation between temperature and carbon dioxide mentioned earlier. For 800,000 years, the carbon dioxide concentration has oscillated between approximately 180 parts per million during glacials and approximately 280 parts per million during interglacials, 100 parts per million difference, roughly a third of the pre-industrial atmospheric concentration of carbon dioxide. and this difference accounts for a significant fraction of the temperature difference between glacials and interglacials. The Vostok and Epica cores also preserve records of methane, another greenhouse gas which similarly tracks the glacial-interglacial cycle, being lower during cold periods and higher during warm ones. The correlation is driven by the extent of tropical wetlands, which produce methane, expanding during warm interglacials and contracting during cold glacials. The ice captures dust from the ancient atmosphere, which varies enormously between glacials and interglacials. The dust record from the Epica core shows that glacial periods had dramatically more atmospheric dust than interglacials, consistent with the cold, dry, windy conditions inferred from other evidence. The dust also provides information about the source regions, and chemical analysis of the dust allows scientists to identify where it came from, tracing the wind patterns of the ancient atmosphere. The ice captures volcanic ash from ancient eruptions, providing a chronological tie points. The sulfate deposited from volcanic eruptions provides a record of major volcanic events stretching back 800,000 years. Glacial ice also records evidence of cosmic events, including supernova explosions whose products are preserved in specific ice layers. The Antarctic ice cores have been joined by Greenland ice cores, which provide complementary records for the Northern Hemisphere. The GRIP and GISP2 cores from Greenland, and more recently the NEEM and NGRIP cores, extend the Northern Hemisphere record back approximately 100,000 years, covering the last glacial cycle in extraordinary detail. These cores show features of the glacial climate in the north that are not clearly seen in the Antarctic record, particularly the rapid climate oscillations within glacials known as Dansgaard-Oeschger events. The Dansgaard-Oeschger events are perhaps the most dramatic rapid climate changes preserved in the ice core record. Within the last glacial period, which lasted from approximately 115,000 years ago to 11,700 years ago, there were at least 25 rapid warming events in the North Atlantic region. Each event involved a temperature increase in Greenland of approximately 10 to 15 degrees Celsius within decades, sometimes within years. The climate switched repeatedly from cold stadial conditions to warm interstadial conditions and then back again, on timescales of centuries to a few millennia. These events were first recognized by the Danish glaciologist Willy Dansgaard and the Swiss geologist Hans Oeschger, who found them in the early Greenland ice cores in the 1980s and 1990s. They are now well-established features of the glacial climate record, seen not only in the ice cores but in marine sediments, cave deposits, and other archives from around the Northern Hemisphere. The mechanism behind Dansgaard-Oeschger events is not fully understood, but the leading hypothesis involves the Atlantic meridional overturning circulation, the same ocean circulation that plays a key role in the Younger Dryas, which we explored in depth in a previous video. During the last glacial period, this circulation was in a different state than it is today, weaker and more vulnerable to disruption by meltwater pulses from the ice sheets. The rapid warmings of the Dansgaard-Oeschger events may represent temporary strengthening of the overturning circulation, bringing warmth to the North Atlantic region, followed by its weakening as the new meltwater from the slightly warmer conditions eventually disrupted it again. The Heinrich events are a related but distinct phenomenon. These are episodes of massive iceberg discharge into the North Atlantic from the Laurentide ice sheet. At intervals of several thousand years during the last glacial period, portions of the Laurentide ice sheet appear to have surged, discharging enormous fleets of icebergs into the North Atlantic. As these icebergs melted, they deposited layers of sediment, called ice-rafted debris, across the floor of the North Atlantic. These Heinrich layers are found in marine sediment cores from the Atlantic and provide a record of the events. The massive freshwater input from the melting icebergs would have disrupted the Atlantic circulation, potentially causing the North Atlantic cooling that often preceded or coincided with major warmings in the Antarctic. The Danskardeuska events and Heinrich events together paint a picture of the glacial climate as highly dynamic and internally variable. Not a static cold period, but a seething, unstable, rapidly changing system in which major regional climate swings could occur within human lifetimes. The stability we associate with the current interglacial, the Holocene, is itself unusual. The past 12,000 years of relative climate stability, which provided the foundation for the development of agriculture and civilization, is not a typical condition of the Earth's climate system. It is an unusually stable, warm period in a history characterized by dramatic variability. Now let's talk about what this cycle had to do with us, with the specific evolutionary and demographic history of our species. Because the 100,000-year heartbeat of the planet did not operate in the background, irrelevant to human history. It shaped human history at its deepest level. The genus Homo appeared approximately 2 to 2.5 million years ago in Africa, exactly during the Pleistocene, exactly during the period when the Ice Age cycles were becoming established as a dominant feature of the Earth's climate. Our evolutionary history is embedded within the Milankovitch framework. We are, in a real sense, children of the Ice Ages. One of the most influential ideas about the connection between climate cycles and human evolution is the variability selection hypothesis, developed by the paleoanthropologist Richard Potts. Potts argued that the key selective pressure driving human cognitive evolution was not any specific climate state, not the cold of glacials or the warmth of interglacials, but the variability itself. The repeated dramatic shifts between climate states, occurring on timescales of thousands to tens of thousands of years, would have repeatedly disrupted the environments that early human populations depended on. The populations that survived were not necessarily the ones best adapted to any specific climate state. They were the ones best able to adjust to rapid change, the ones with the cognitive flexibility to shift dietary strategies when the food sources they depended on disappeared, the ones with the social organization to maintain group cohesion through periods of resource stress, the ones with the technological capacity to solve new problems as the environment created new problems to solve. In this view, human intelligence is not adaptation to any specific environment. It is adaptation to environmental change itself. The rapidly cycling Milankovitch climate is what created the selection pressure for the extreme cognitive flexibility that defines our species. We are smart because the planet kept changing the rules. The African humid periods are a specific application of this idea to the question of human dispersals. Africa experienced alternating wet and dry periods, driven by the same Milankovitch forcing that drove ice ages in the northern hemisphere. During humid periods, the Sahara greened, lake levels rose, the Nile Valley corridor became passable. The barriers that normally confined human populations to sub-Saharan Africa opened. The genetic evidence of human migrations out of Africa and of population expansions and contractions within Africa shows a pattern that corresponds broadly to these climate cycles. Major dispersals appear to coincide with periods of improved environmental conditions, green corridors opening through what were otherwise impassable barriers. The out-of-Africa migration that gave rise to all non-African modern humans is estimated by genetic methods to have occurred approximately 50 to 70,000 years ago. This timing corresponds to a period of relatively favourable climate conditions in northeast Africa and the Near East, a green corridor opening through the Levant as the monsoon system strengthened and the Sahara was wetter than today. But there were earlier dispersals too. The fossil and genetic evidence suggests that modern humans reached the Levant much earlier, perhaps 120,000 years ago, during the previous interglacial when conditions were again favourable. Those early dispersers apparently did not give rise to surviving populations outside Africa. They may have been replaced by Neanderthals as climate deteriorated and the Levantine corridor closed again. The timing of human coastal migrations, of the dispersal into Southeast Asia and Australia, of the eventual crossing of Beringia into the Americas, all of these show relationships with climate cycles, with sea levels, with the opening and closing of routes that depended on sea level and vegetation cover. The geography of the Ice Age world, with its lower sea levels and different vegetation zones, created specific migration pathways that did not exist during interglacials. The peopling of the Americas, which could only have occurred when the Bering Land Bridge was exposed by low sea levels, happened during a glacial period when the bridge was available but when glacial conditions also created other barriers further south. The Milankovitch cycles are therefore not just a feature of Earth's physical history, they're a feature of our own biographical history as a species. The specific timing of our evolutionary transitions, our geographic dispersals, our encounters with other human groups, all of these were shaped by the rhythmic cycling of the planet's climate, driven by the astronomical cycles that Milankovitch calculated by hand in a Budapest library during the First World War. Let us now talk about the most dramatic moment in the cycle, the termination. The termination is the name given to the end of a glacial period, the transition from the cold extreme of the cycle to the warm interglacial. There have been 8 terminations in the Epocha record, and each one has been studied in detail for what it can tell us about how the climate system shifts from one state to another. The terminations are not gentle transitions. They're among the most dramatic events in the climate record. The temperature change from glacial maximum to interglacial, measured in Greenland ice cores, is approximately 10 to 15 degrees Celsius. Sea levels rise by approximately 120 meters. The ice sheets that covered tens of millions of square kilometers of the Northern Hemisphere disappear. The biomes reorganize. It is by any measure a planetary transformation, and it happens relatively fast. The most rapid phase of deglaciation during the last termination, approximately 14,000 to 11,000 years ago, saw sea levels rising at rates of up to 4 meters per century during the most intense phases. Meltwater pulses, episodes of rapid ice sheet collapse, are recorded in the sediment record as sudden jumps in sea level. Meltwater pulse 1A, approximately 14,600 years ago, may have seen sea levels rise by approximately 20 meters in less than 500 years, 4 centimeters per year, continuous, relentless, transforming every coastline on the planet. What triggers the termination? This is a question that has consumed an enormous amount of research effort. The broad answer is that the termination begins when the astronomical configuration starts to favour warming at high northern latitudes during summer. The specific combination of orbital parameters, primarily the obliquity and precession, that produces peak insolation during Northern Hemisphere summer is the trigger. The ice sheets, which have grown large and extensive over the preceding 90,000 years, are now receiving their maximum summer solar heating, and the ablation rate begins to exceed the accumulation rate. But the termination is not simply the reverse of the build-up. The dynamics are different. The ice-albedo feedback, which runs in reverse during termination, is joined by other feedbacks that make the collapse self-reinforcing. The carving of ice into the ocean as ice sheets reach tidewater becomes increasingly important as the ice extends to the continental margins. The carbon dioxide feedback, as the warming ocean releases the greenhouse gas that then amplifies the warming, is one of the most powerful amplifiers of the termination signal. There is also the role of the deep ocean, which warms slowly during glacials, and then begins to release its stored heat during termination, providing additional energy for ice sheet melting. The interplay between the surface climate, the ice sheets, the ocean, and the atmosphere during a termination is extraordinarily complex, involving feedbacks and interactions on multiple timescales simultaneously. The last termination, which ended the most recent glacial and ushered in the Holocene, is the most thoroughly studied. It proceeded in multiple steps, with periods of rapid warming alternating with reversals. The Younger Dryas, which we explored in detail in a previous video, was a dramatic reversal within the last termination, a brief but intense return to near glacial conditions approximately 12,900 years ago, driven by the disruption of the Atlantic overturning circulation by meltwater from the retreating ice sheets. After the Younger Dryas ended abruptly approximately 11,700 years ago, the final push of the termination was rapid and complete. Within a few thousand years, the great ice sheets of the Northern Hemisphere were reduced to approximately their current extents. The last remnants of the Laurentide ice sheet over the Hudson Bay region disappeared approximately 7,000 years ago. The global sea level reached approximately its current level by about 7,000 years ago and has been relatively stable since. The Holocene, the warm interglacial we currently inhabit, began at the end of the Younger Dryas. Approximately 11,700 years ago, the climate shifted, rapidly and dramatically, to the warm, stable conditions under which all of human civilization has developed. Agriculture, cities, writing, philosophy, science. All of it happened within a single interglacial, the most recent warm phase in the 100,000-year cycle. The timing of the transition to the Holocene is not coincidental with the development of agriculture. It is causal. The stable, warm, wet conditions of the early Holocene, particularly in the Fertile Crescent and in other centres of agricultural origin, are what made agriculture possible. The climatic instability of the glacial period and the late Pleistocene, with its Dansgaard-Oeschger events and Heinrich events and Younger Dryas reversals, would have made the investment in permanent agriculture too risky. Why invest in a crop and a field if the climate might change dramatically within your lifetime? The unusual stability of the Holocene, a feature of interglacial climate, created the conditions in which the multi-year investment of agriculture became viable. We did not develop civilization in spite of the Milankovitch cycles. We developed it because of them, because the most recent one created a window of stability long enough and warm enough for the accumulated cultural knowledge of our species to cross the threshold into something that could organize itself beyond the hunter-gatherer scale. Let us think for a moment about what it felt like to live through the end of the last glacial and the beginning of the Holocene. Not the statistics, the experience. You are a hunter-gatherer in what is now the Middle East, approximately 13,000 years ago. The climate over the past few thousand years has been improving. The Younger Dryas has not yet arrived, though it will come in a few centuries. The vegetation in your region is expanding. The wild grains that your group has been harvesting intensively are more abundant than they have been in living memory. The water sources are more reliable. Your grandparents would have told you stories of harder times, when the grasslands were thinner and the game less reliable, when the group sometimes had to move further and work harder to feed itself. The stories they told were not myths. They described conditions within human memory, within the span of a few generations, when the climate was different enough from the present, that the specific knowledge your group has accumulated about the local landscape was less reliable. This is the memory of the Ice Age world. Not the glacial maximum itself, which was too long ago and too extreme for living memory to reach, but the variable, unpredictable climate of the late glacial, the oscillations and reversals, the sudden changes that made the accumulated ecological knowledge of one generation partially obsolete for the next, the cultural memory of instability. And now the world was improving. The summers were warmer, the winters were less severe, the wild grains grew in larger patches. The groups that had been most intensively managing their relationships with specific plant and animal populations were finding that this intensification was paying off, that the investment in knowing exactly where the grain grew and when to harvest it, and which patches to protect and which to leave alone was producing reliable food, in a way that the older, more mobile strategies could not match in a world this productive. Then the Younger Dryas arrived. Within a few decades, the warming trend reversed. The grasslands contracted. The wild grain patches shrank. The water sources became less reliable. A way of life that had been building towards something more permanent, towards something approaching proto-agriculture, was disrupted. Groups that had been settling near reliable food sources had to move again or intensify their management of dwindling resources. The Younger Dryas lasted 1,200 years, long enough that the living memory of the warm period before it faded, long enough that the groups which had been moving toward proto-agricultural strategies had to develop new adaptations, long enough that what had seemed like the beginning of a new way of living was interrupted and had to be reinvented. And then, abruptly, the Younger Dryas ended. The climate shifted back to warm conditions, more abruptly than even the shift into the cold had been. Within decades, the grasslands were expanding again. The wild grains were growing in dense, productive patches. The rivers were running reliably. The world was warmer and wetter than it had been before the Younger Dryas began. This time, the intensification of plant management, the proto-agricultural practices that had been disrupted by the cold, were taken further. Perhaps because the groups that had invested in specific locations and specific plant management strategies during the warm period before the Younger Dryas had maintained the knowledge of those strategies through the cold, even if they could not practice them fully. Perhaps because the disruption of the Younger Dryas had demonstrated the value of having more reliable food sources. Perhaps simply because the conditions were now right and the knowledge was there, and the critical mass of accumulated innovation finally crossed the threshold. Within a few thousand years of the end of the Younger Dryas, the first agricultural communities had appeared in the Fertile Crescent. Within 10,000 years, agriculture had spread across the world. Within 12,000 years we are here. the product of an agricultural revolution that was triggered by the end of the most recent Milankovitch cycle, the transition from glacial to interglacial that makes the 100,000-year planetary heartbeat feel personal, feel relevant, feel like part of our own story, because it is. Here is a question that might feel more immediate than the ice ages of the deep past. Are we overdue for the next one? Is the next glaciation already beginning? And what has human activity done to the timing of the cycle? These are genuine scientific questions with real answers, or at least real partial answers, constrained by what we know about the orbital configuration and the dynamics of the climate system. The Milankovitch cycles continue. The Earth's orbit and rotation axis are doing what they always do, slowly changing their geometry under the influence of the other planets. The current orbital configuration, the specific combination of eccentricity, obliquity, and precession that we are currently experiencing, is one that would, absent human influence, be expected to lead to the next glaciation in approximately 50,000 years. This estimate comes from the detailed analysis of the orbital parameters and their relationship to the timing of past glaciations and interglacials. The current interglacial, the Holocene, is in some respects already quite long by historical standards, having lasted approximately 11,700 years. But the comparison to the Stage 11 interglacial 400,000 years ago, which lasted approximately 30,000 years under a similar orbital configuration, suggests that the current interglacial might naturally last another 10 to 20,000 years before the next glaciation would begin. This is a natural estimate. It assumes that the climate system would behave as it has in the past, responding to the Milankovitch forcing in the same way. That assumption is no longer valid. The current atmospheric carbon dioxide concentration, over 420 parts per million, is higher than at any point in the past 800,000 years of ice core records. The natural forcing associated with this level of carbon dioxide is sufficient to significantly delay or suppress the next glaciation. A paper published in 2016 in the journal Nature estimated that human carbon dioxide emissions have delayed the next glaciation by at least 50,000 years, and possibly much longer depending on how much total carbon is ultimately emitted. This is not, in the context of this discussion, a simple cause for relief. The prevention of the next ice age is a side effect of a carbon dioxide increase that is occurring at a pace and to a magnitude that the Earth system has not experienced in millions of years, and whose primary near-term consequences are not welcome ones. The prevention of the next glaciation in 50,000 years does not offset the changes occurring now. But it is a genuine and verifiable statement about the relationship between human activity and the Milankovitch cycle. For the first time in the history of our species, we have altered the rhythm of the planetary heartbeat. We have disrupted significantly the 100,000-year pattern that shaped our evolution, shaped our history, shaped every human civilization that has ever existed. The cycle that made us is now running differently because of us. That is an extraordinary thing to hold in your mind, not necessarily a comforting thing, not necessarily a terrifying thing, an extraordinary thing. The species that the Milankovitch cycles helped create has now become inadvertently, an agent acting on those same cycles. We are no longer only receivers of the planetary signal. We are transmitters. Let me bring the threads together now. Let me say what the 100,000-year cycle actually means, beyond the specific science, for understanding our relationship to the planet we live on. This cycle is real. The ice cores prove it. 800,000 years of evidence, 8 complete cycles, the same basic template repeated over and over with variations, but with a recognizable fundamental rhythm. The planet cools slowly, builds ice, modifies its own climate through the albedo feedback and the carbon cycle feedback. And then, when the orbital configuration finally tips in the right direction, collapses rapidly into a warm interglacial. Then the slow cooling begins again. The mechanism is astronomical in its trigger but planetary in its expression. Milankovitch identified the trigger. But the climate system responds to that trigger through feedbacks, through the ice-albedo mechanism and the carbon dioxide mechanism and the ocean circulation mechanism that amplify a small astronomical signal into a large planetary climate change. The astronomical forcing sets the rhythm. The Earth system sets the amplitude. The response is not passive. The Earth system does not simply respond proportionally to the astronomical signal. It has thresholds. It has bistable states. It can be in a glacial mode or an interglacial mode, and the transition between modes can happen much faster than the orbital forcing that drives it. This nonlinearity is why the terminations are rapid, even though the orbital forcing changes slowly. The system crosses a threshold, and then the feedbacks take over, driving rapid change. The mid-Pleistocene transition shows that the Earth system can change its mode of response to astronomical forcing. Before 1 million years ago, the climate responded to the 41,000-year obliquity cycle. After the transition, it responded to the 100,000-year eccentricity cycle. The forcing was the same. The response changed because the Earth system itself evolved, probably through the gradual erosion of regolith and the progressive cooling of the deep ocean over millions of years of Pleistocene glaciations. The 100,000-year problem shows that we do not fully understand why the system responds the way it does. The dominant frequency of the response is not what simple physics would predict. The Earth system has its own internal dynamics that interact with the astronomical forcing in ways that are not fully captured by simple linear models. And the human angle shows that the cycle is not merely historical. It is present and future. Our civilization was built within the current interglacial. Our agriculture, our cities, our infrastructure, our entire way of organizing human life is calibrated to the climate of the Holocene. The Milankovitch cycle will not be the next glaciation that threatens this. The carbon dioxide we have added to the atmosphere has altered the equation in the near-term direction that is itself a challenge. But understanding the deep cycle, understanding the rhythm that shaped our species and our history, is part of understanding what it means to live on a planet that is not static, that is always in process, always changing, always somewhere in its 100,000-year heartbeat. The ice will come again. Perhaps not in 50,000 years now. Perhaps not in the same way. But the astronomical forcing will continue. The eccentricity will cycle. The obliquity will change. The precession will wobble. The rhythm that Milankovitch calculated by hand in Budapest will keep running, as it has run for tens of millions of years, as it will run for tens of millions more. We are creatures of one particular phase of that rhythm. We evolved during the Pleistocene glaciations. We civilized during the Holocene interglacial. We altered the carbon cycle during the Industrial Age. Our relationship to the 100,000-year cycle has been first passive, then biological, then agricultural, and now geological. We have become a force on the system that made us. What we do with that fact, what responsibilities it generates, what understanding it requires, those are questions for the species that will inherit the consequences of our current phase. But the fact itself is established. The cycle is real. The record is in the ice, and our place within it is far more central and far more consequential than most of human history has recognized. Before we go deeper into what the cycle looks like from the inside, let us talk about the other great archive besides the ice cores, the one that covers a longer span of time, that provided the first real vindication of Milankovitch's theory, and that is in some ways even more extraordinary as a natural record-keeping system. The ocean floor. The deep ocean floor is one of the most stable and undisturbed environments on Earth. Far from the turbulence of the surface, far from the erosion and disruption that removes or alters most geological records on land, the deep ocean floor accumulates sediment in a continuous, undisturbed succession. Year by year, century by century, millennium by millennium, particles drift down from the surface water above and settle gently on the ocean floor. The particles include the shells and skeletal remains of the organisms that lived and died in the surface ocean, the fecal pellets of zooplankton clay carried by rivers or wind from the continents, volcanic ash from eruptions, and cosmic dust from space. Over millions of years, these particles accumulate in layered sequences that are, in many locations, beautifully preserved and continuous. By drilling into the ocean floor and extracting sediment cores, scientists can recover these sequences and read them year by year and century by century as a record of what the ocean and the climate were doing at any given time in the past. The organisms most useful for paleoclimate reconstruction from deep-sea cores are the foraminifera. Foraminifera are single-celled organisms that live in the surface ocean, building intricate shells from calcium carbonate. When they die, their shells sink to the ocean floor and accumulate in the sediment. Because foraminifera are sensitive to temperature, salinity, and other oceanographic conditions, the composition of the foraminiferal assemblage in a sediment layer records the conditions at the surface ocean when those organisms were alive. Different species of foraminifera prefer different temperatures. The relative abundance of different species in a sediment layer therefore tells you about the temperature of the surface ocean when that layer was deposited. More powerfully, the chemical composition of individual foraminiferal shells records environmental conditions with remarkable precision. The ratio of oxygen 18 to oxygen 16, the same proxy used in the ice cores, is incorporated into the calcium carbonate of the shell as the organism builds it, and it reflects both the water temperature and the global ice volume at the time of shell formation. By measuring this ratio in thousands of carefully picked fossil foraminifera from precisely dated sediment layers, scientists can reconstruct the continuous history of ocean temperature and global ice volume going back millions of years. The landmark study that vindicated Milankovitch's theory was published in 1976 by James Hayes, John Imbrie, and Nicholas Shackleton in the journal Science. The paper was titled Variations in the Earth's Orbit, Pacemaker of the Ice Ages. It used oxygen isotope records from deep-sea sediment cores to demonstrate using spectral analysis that the Ice Age record contained statistically significant power at exactly the frequencies predicted by Milankovitch theory. The periods of the obliquity cycle, the precession cycles, and the eccentricity cycle all appeared in the climate record with unambiguous statistical confidence. The pacemaker paper, as it is known, is one of the most important papers in all of climate science. It demonstrated that the astronomical theory of ice ages was not just plausible but correct. The climate system was responding to the Milankovitch forcing. The timescales matched, the frequencies matched. The theory that a Serbian mathematician had spent decades developing was confirmed in the data from the ocean floor. But the pacemaker paper also revealed what would become the 100,000-year problem. The power at the eccentricity frequency, approximately 100,000 years, was the largest signal in the record. The obliquity signal was there but smaller. The precession signals were there but smaller still. The dominant climate response was at the frequency of the weakest forcing. This paradox has been the central puzzle of Milankovitch theory ever since, and it has driven decades of research into the ice sheet dynamics, ocean circulation, carbon cycle feedbacks, and non-linear system behavior that might explain why the weakest astronomical signal produces the strongest climate response. The ocean sediment cores do not just give us the climate signal, they give us the biological signal. The specific assemblages of foraminifera, diatoms, coccolithophores, and other microfossils preserved in the sediment record the ecological history of the surface ocean. The changes in assemblage composition from glacials to interglacials and back again tell us about how the ocean ecosystem reorganized in response to the climate changes. During glacials, the polar fronts, the boundaries between cold polar water and warmer mid-latitude water, expanded toward the equator. The productive waters that form at polar fronts, where nutrient-rich deep water is brought to the surface, were located further from the poles. The distribution of phytoplankton blooms changed. The zooplankton that fed on the phytoplankton responded. The fish that fed on the zooplankton responded. The entire food web of the ocean was restructured by the climate change. The most vivid expression of this restructuring is visible in the distribution of certain key species. The polar foraminifera Neogloboquadrina pachyderma, which today is found only in very cold water near the poles, extended its range far toward the equator during glacial maxima. Sediment cores from the North Atlantic show this species dominating at latitudes where today only warm water species are found. The cold water had followed the ice southward, carrying its characteristic organisms with it. Conversely, warm water species that today range into the North Atlantic were largely absent from the glacial North Atlantic, having retreated toward the tropics as the cold expanded. The ocean was a different place, not just colder, but ecologically reorganized from top to bottom, and the recovery of the ocean ecosystem during terminations tracked the physical recovery of the climate. As waters warmed and ice retreated, the polar fronts withdrew northward. The warm water species recolonized the North Atlantic. The cold water specialists retreated back toward the poles. The ecosystem restructured itself, following the physics of the ocean as the Milankovitch forcing drove the system toward an interglacial state. This biological reorganization is one of the most profound examples of how life and climate are coupled on the planet. The organisms of the ocean are not passive residents of a physical environment. They are active participants in the climate system, their photosynthesis drawing down carbon dioxide, their biological pump exporting organic carbon to the deep ocean, their calcification producing the shells that record climate history, and in so doing, through their dissolution and preservation, modifying ocean chemistry. The Ice Age cycle is not just a physical and chemical phenomenon, it is a biological phenomenon too. Let us talk about what the ice sheets themselves were like from the inside. The Laurentide ice sheet at its maximum was a structure so large and so heavy that it is difficult to comprehend in any intuitive way. A dome of ice approximately 3 to 4 kilometers thick at its centre, covering all of Canada and extending south to roughly the Ohio River in the United States. The ice was not static, it was moving, flowing outward from its central dome under its own weight, advancing slowly at its margins in some places and retreating in others, depending on the balance between accumulation in the interior and melting at the edges. At the base of the ice sheet, in direct contact with the rock below, the ice was at the pressure melting point, meaning the enormous pressure of the overlying ice lowered the melting point of the ice enough that a thin film of liquid water existed. This basal meltwater lubricated the contact between the ice and the bedrock, allowing the ice to slide over the underlying surface. The sliding left its signature in the rock beneath, the striations, the polish, the characteristic landscapes of glacially carved terrain that are visible today across Canada, Scandinavia, and northern Europe. The surface of the ice sheet was not the smooth, featureless plane that simplified illustrations often show. It was a complex landscape of its own. Crevasses opened where the ice moved over irregular terrain below. Surface meltwater in summer formed pools and rivers on the ice surface, called supraglacial lakes and streams, that often drained catastrophically through moulins, vertical drainage channels that carried the surface water to the base of the ice. These drainage events could be sudden and dramatic, emptying lakes that had accumulated for weeks or months in minutes. At the margins of the ice sheet, where the ice was thin and active, enormous quantities of rock debris accumulated during the slow transit of the ice from the interior were deposited as the ice melted. Moraines, the ridges and hills of glacial sediment, mark the positions of former ice margins. End moraines mark the farthest advance of the ice. Lateral moraines mark the sides of valley glaciers. Drumlins, streamlined hills of glacial sediment, were shaped by the flow of ice over soft sediment. The entire landscape of formerly glaciated regions is a record of the ice sheet, its extent, its movement, its dynamics. The ice sheets also had a profound influence on the regional climate. The cold, dense air over the ice sheets sank and flowed outward, creating strong and persistent wind patterns that affected precipitation and temperature over large areas. The ice sheets altered the position of the jet streams, those high-altitude rivers of wind that steer weather systems. The glacial circulation patterns were different from today's in ways that profoundly affected where rain fell and where drought prevailed. The monsoons were weaker. The trade winds were in different positions. The entire atmospheric circulation was organized around the presence of enormous cold masses of ice in the northern hemisphere. When the ice retreated during a termination, the atmospheric circulation reorganized in response. Regions that had been dry became wet. Regions that had been wet became drier. The monsoon strengthened. The trade winds shifted. Vegetation zones that had been pressed toward the equator by the cold expanded back toward the poles. It was a global reorganization of weather patterns driven by the disappearance of the ice. Let us also talk about the megafauna. Because the ice ages and the megafauna are inseparably linked, and the fate of the megafauna at the end of the last glacial is one of the most debated questions in quaternary science. The megafauna of the Pleistocene, the large animals, those over 44 kilograms, were remarkably diverse in the late Pleistocene. Across North America, woolly mammoths and mastodons, ground sloths the size of elephants, giant beavers, short-faced bears, American lions, dire wolves, horses, camels and tapirs formed a diverse guild of large animals. In Eurasia, woolly mammoths and woolly rhinoceroses shared the mammoth steppe with cave bears, cave lions, and giant deer with antlers spanning 4 meters. In Australia, enormous marsupials, including the car-sized diprotodon and giant kangaroos, inhabited the continent alongside massive monitor lizards and flightless birds. In South America, toxodons, giant ground sloths, glyptodonts, and macrauchenia added to the diversity of an isolated continent. Then, between approximately 50,000 years ago and 10,000 years ago, most of these animals went extinct. The timing and pattern of extinctions differ by continent in ways that have been intensely studied and debated. In Australia, the major extinctions occurred around 50,000 years ago, coinciding with the arrival of the first humans on the continent. In North America and South America, the extinctions occurred around 13 to 12,000 years ago, coinciding with both the arrival of humans on those continents and the rapid climate change at the end of the last glacial. In Africa and tropical Asia, the megafauna survived relatively better, an observation attributed to the longer coexistence of large animals with evolving hominins on those continents, which gave the animals time to develop wariness of human hunters. The cause of the megafauna extinctions is one of the most heated debates in paleontology and ecology. The 2 primary hypotheses are overkill and climate change, and the debate between them has been going on for decades with no fully decisive resolution. The overkill hypothesis, associated primarily with the ecologist Paul Martin, argues that human hunters were the primary cause. Modern humans are extraordinarily effective hunters of large, slow-reproducing animals. In Africa and tropical Asia, where large animals had evolved alongside hominins for millions of years, the animals had developed wariness of humans and the hunting pressure was sustainable. On continents and islands where large animals had no evolutionary experience with human hunters, they were naive and easy to hunt. Human populations could have driven even the largest mammals to extinction within centuries of arrival, simply by hunting more individuals than the populations could replace. The climate change hypothesis argues that the rapid climate changes at the end of the last glacial, the dramatic restructuring of vegetation zones and the loss of specific habitat types like the mammoth steppe, drove the megafauna to extinction by destroying the ecosystems they depended on. The mammoth steppe, the specific cold grassland ecosystem that supported mammoths and other large grazers across Eurasia and North America, does not exist today. It was replaced by boreal forest in the north and temperate grassland further south. Animals adapted to mammoth steppe conditions had nowhere to go when the climate changed. The current scientific consensus leans toward an interactive explanation. Both climate change and human hunting played roles, and the relative importance of each varied by continent, by species, and by timing. In many cases, the climate change had already stressed and reduced megafauna populations before human hunters arrived, making those populations more vulnerable to the additional pressure of hunting. The combination of both stresses was more lethal than either alone. What is relevant here is the Milankovitch context, the termination of the last glacial, the rapid climate change that replaced the mammoth steppe with forest and grassland was a Milankovitch scale event. It was the astronomical forcing, amplified by the ice-albedo and carbon dioxide feedbacks, that drove the rapid warming that reorganized the terrestrial biomes, and that reorganization, combined with the presence of a newly arrived and highly effective predator, ended the Pleistocene megafauna. Every 100,000-year cycle produces such a termination. Every termination reorganizes the terrestrial biomes. Every reorganization stresses the organisms adapted to the glacial world. The extinctions at the end of each glacial, for organisms that could not track the shifting biomes fast enough, are a recurring feature of the Milankovitch cycle. The last termination was unusual only in that it coincided with the global spread of modern humans, adding a second, unprecedented stressor on top of the recurring stress of climate change. There is a second CTA moment here, because we are now deep into the story and approaching the final sections. If you have listened this far and found yourself genuinely engaged, please subscribe if you have not already. These are the kinds of stories that take real research and real time to put together properly. A subscription helps make the next one possible. And now, the last pieces of the puzzle. The solar connection to the 100,000-year cycle is sometimes raised as an alternative explanation for ice ages. Could variation in the sun's output, rather than variation in the Earth's orbital geometry, explain the glacial cycles? This has been extensively investigated, and the answer is essentially no, at least for the 100,000-year cycles. Solar output does vary on multiple timescales. The 11-year sunspot cycle produces small variations in solar output. Longer cycles of solar activity, spanning centuries, like the Maunder minimum of the 17th century when sunspot activity was unusually low, produce larger but still modest variations. Over millions of years, the sun has slowly brightened, by approximately 7% over the past billion years, as part of its natural stellar evolution. But none of these solar variations match the Milankovitch timescales. The 11-year sunspot cycle is far too short. The centennial variations are too short and too small. The long-term brightening is far too slow and in the wrong direction to explain the Ice Age cycles. The astronomical evidence for the Milankovitch cycles as the pacemaker of ice ages, established by the pacemaker paper and confirmed by decades of subsequent research, is robust and does not require solar output variation as an additional explanation. The ice ages are an orbital phenomenon amplified by Earth system feedbacks. The sun's role is to provide the constant background radiation that the orbital changes modulate. The sun is the energy source. The Milankovitch cycles are the modulation. The ice-albedo and carbon dioxide feedbacks are the amplifiers. All three are necessary. The Milankovitch cycles without the solar energy would do nothing. The solar energy without the Milankovitch modulation would produce no glacial cycles, and without the feedbacks, the orbital forcing would be too small to produce the observed magnitude of glacial-interglacial change. Understanding this three-part structure, forcing plus modulation plus amplification, is important for understanding why the current situation is different from anything in the Milankovitch record. The solar energy is unchanged. The Milankovitch modulation is operating normally, currently in a phase that would naturally favour a very slowly cooling trajectory toward the next glaciation over tens of thousands of years. But the carbon dioxide feedback is operating at an unprecedented level, driven by human emissions rather than by orbital ocean dynamics. The amplification system is being driven by a new input that the 100,000-year record does not contain. The climate system responds to the sum of all forcings and feedbacks. In the past 800,000 years, that sum was dominated by the Milankovitch-driven oscillation, with carbon dioxide as an amplifier of that oscillation. Now the carbon dioxide component has been decoupled from the Milankovitch oscillation and driven to levels outside the range of the natural amplification, The climate system is receiving an input that has no precedent in the ice core record. Predicting how it will respond requires extrapolating beyond the calibration range of the natural record, which is one of the core challenges of climate science. The ice cores provide the best constraint we have. They tell us what the climate did under specific carbon dioxide concentrations in the past. They tell us what the temperature change per unit of carbon dioxide increase has been historically. And they tell us that the magnitude of carbon dioxide change we've produced in the industrial era is far larger than anything in the past 800,000 years of natural climate variation, not 2 or 3 times larger, more than 40% above the natural maximum of approximately 280 parts per million. That is an extraordinary perturbation to a system whose natural dynamics we understand, at least partly, through the lens of its own history. We have pushed the system outside its historical envelope. What happens next is something the ice cores cannot fully tell us, because nothing comparable has happened in the timespan they cover. What they can tell us is that carbon dioxide is a powerful amplifier of temperature change, that the climate responds to it on multiple timescales from decades to millennia, and that changes of the magnitude we've introduced take a long time for the full climate system to express. The ocean has a thermal inertia. The ice sheets have a dynamic inertia. The vegetation and soil systems have inertia. The full response to the current carbon dioxide forcing has not yet been expressed. It is in the pipeline. The 100,000-year cycle will continue, whatever we do. The astronomical mechanics are not affected by human activity. In the very long run, tens of thousands of years hence, the ice will come again, or it will not, depending on what the atmospheric carbon dioxide is at that time and on the specific orbital configuration then prevailing. The glacial cycle is not broken, it is perturbed. The perturbation is large by historical standards, but the astronomical clock keeps ticking. Let us look at the broader context of what the Milankovitch cycles are part of. Because the 100,000-year cycle, real and important as it is not the only timescale of climate variation. The Earth's climate varies on every timescale, from the daily heating and cooling of the surface to the 100-million-year timescales of plate tectonic reorganization and the evolution of the solar luminosity. The Milankovitch timescales sit in the middle of this hierarchy, shorter than the tectonic timescales, which drive the slow drift of continents, the opening and closing of ocean basins, the growth and erosion of mountain ranges that alter atmospheric circulation and regional climate, longer than the centennial to millennial timescales of ocean circulation variability and internal atmospheric dynamics. The tectonic context matters for the Milankovitch cycles because the long-term tectonic configuration determines the baseline climate state within which the Milankovitch oscillations operate. In warm, ice-free periods of Earth history, like the Cretaceous period when dinosaurs were alive and the global mean temperature was perhaps 10 to 14 degrees warmer than today, the Earth had no significant polar ice sheets. Without ice sheets, the ice-albedo feedback that amplifies the Milankovitch forcing during cold periods is absent or greatly reduced. The Milankovitch cycles still affected climate during these warm periods, but without the ice-albedo amplification, their effect was much smaller. Tropical ocean temperatures varied. Monsoons changed in intensity. Sea levels rose and fell, but glaciations of the magnitude of the Pleistocene simply did not occur. The Pleistocene Ice Age world, the world of the past 2 to 3 million years with its dramatic glacial interglacial cycles, exists because the tectonic configuration of the current era has put ice sheets at both poles. Antarctica became permanently glaciated approximately 34 million years ago, when the separation of Antarctica from South America by plate tectonics opened the Drake Passage, allowing the circumpolar current to develop and thermally isolate the continent. The Arctic Ocean basin was largely enclosed by the late Neogene, creating the cold, relatively fresh surface waters that allow sea ice to form, and the uplifting of the Tibetan Plateau by the collision of India with Asia may have altered global atmospheric circulation in ways that contributed to the planetary cooling trend of the past 50 million years. We are living in an icehouse world, a technical term for an era when polar ice sheets are present and glaciations are possible. The Milankovitch cycles, whose effects are dramatic in the current icehouse, would have been much smaller perturbations in the greenhouse world of the Cretaceous. The same astronomical forcing, the same orbital mechanics that Milankovitch calculated, but a very different climate response because the Earth system was in a different baseline state. The transition from greenhouse to icehouse over the past 50 million years is a reminder that the current Pleistocene pattern, however dramatic it seems on human timescales, is itself a phase in an even longer planetary story. The Milankovitch cycles have been operating throughout Earth's history. Their expression in climate has varied enormously depending on the baseline configuration of continents, oceans, and ice. What this means is that the future of the 100,000-year cycle is not fixed by the astronomical mechanics alone. It depends on the tectonic context, which changes slowly, and on the atmospheric composition, which is currently changing fast. If the planet remains in an icehouse configuration, and if atmospheric carbon dioxide returns to natural Milankovitch range values, the glacial cycles will resume on their historical schedule. If the carbon dioxide remains elevated for geological timescales, as it will if human emissions continue at current rates for much longer, the icehouse may transition toward a warmer state in which glaciations are suppressed or altered. These are not imminent changes in the sense of decades, but they are real trajectories that the Earth system follows on its own timescales, which are long by human standards but short by geological ones. Understanding where the Earth system is in the space of possible states, and how far from its historical envelope our current perturbation has pushed it, is one of the most important scientific questions of our era. The 100,000-year cycle is our clock. It set the rhythm of our evolution, our history, our civilization. Knowing how that clock works, knowing where we are in the cycle and what the cycle's future looks like, is part of knowing who we are and where we are going. There is a deeper connection between the 100,000-year cycle and something we have explored at length before, a connection that ties the astronomical story to the human story in a way that is both scientifically specific and personally resonant. The Younger Dryas, the abrupt reversal that interrupted the last termination approximately 12,900 years ago, was itself a product of the Milankovitch cycle. It was not caused by the cycle directly. It was caused by the dynamics of ice sheet melting triggered by the cycle. The Laurentide ice sheet, responding to the orbital forcing of the last termination, had been melting for several thousand years by the time of the Younger Dryas onset. The meltwater from that melting, accumulating in the glacial lakes along the ice sheet's southern margin, eventually found a drainage route to the Atlantic and disrupted the overturning circulation. In other words, the Younger Dryas was a consequence of the termination, and the termination was a consequence of the Milankovitch forcing. The event that almost ended human prehistory, the catastrophe that may have reduced the human population by 90% and destroyed the cultural complexity that had been developing for thousands of years, was ultimately a byproduct of the astronomical cycle that Milankovitch calculated. The 100,000-year heartbeat did not kill only the megafauna and reorganize the biomes. It also, through the mechanism of the last termination, nearly killed us. We are here not despite the Milankovitch cycle, but because of it, and also surviving in spite of the most dangerous moment it created in our specific evolutionary history. The cycle that made us by driving our cognitive evolution across millions of years of glacial climate variability also nearly unmade us in its most recent termination event. That is a profound irony. Or perhaps not an irony at all, but simply the nature of the world. The same forces that create also destroy. The same astronomical mechanics that drove the Pleistocene climate variability that selected for human cognitive flexibility also drove the termination dynamics that produced the Younger Dryas that killed 90% of our ancestors. The same cycle, different moments, different expressions of the same underlying physics. Understanding this connection is part of why the Milankovitch story matters beyond academic paleoclimatology. It is part of the deep context of our existence. The astronomical cycles that were operating long before our species existed, that will operate long after we are gone, intersected with our history at specific moments that shaped who we are and what we survived. We are not independent of those cycles. We are embedded in them. The current moment of departure from the natural Milankovitch range is therefore not just an environmental issue in the narrow sense. It is a departure from the framework within which our species evolved, the framework within which our civilization was built. We are adapting the planet to new conditions as our carbon dioxide emissions push the climate system outside the envelope of the Milankovitch oscillation, even as we are still biologically creatures of the Milankovitch world. Creatures built for variability, yes, but variability within a specific range and on specific timescales. The variability we're introducing is different in character, faster in onset, and potentially larger in magnitude than the natural Milankovitch variability that shaped us. There is also the question of what the next generations of ice core science will reveal. The current deep ice core record extends back 800,000 years. Below the depth of the Epica Dome sea core, the ice is under such pressure that the annual layers are compressed and the temporal resolution is lost. But there are Antarctic sites where the ice thickness is greater and where the bedrock topography may have preserved very old ice in an almost undisturbed state. The Beyond Epica project, a European consortium currently working on a new ultra-deep ice core at a site called Little Dome Sea, aims to recover ice that may be as old as 1.5 million years. If successful, this core will cover the mid-Pleistocene transition itself, providing the ice core record of the shift from 41,000-year to 100,000-year glacial cycles. The mid-Pleistocene transition ice core record would be transformative for understanding the 100,000-year problem. The ice core data before and after the transition, the atmospheric composition, the temperature, the dust, the methane, preserved in ice from the transition period itself, would provide direct evidence of what changed in the Earth system as the dominant mode of glaciation shifted. The climate scientists who are developing the methods and the equipment for this project are working on one of the most important problems in Earth science. The answer to why the cycle changed may be in the ice, waiting to be extracted and read. The science of the Milankovitch cycles is not finished. It is mature in the sense that the basic framework is well established and widely accepted, but it is still producing new discoveries, still confronting genuinely open questions, still being extended in time and refined in resolution. The 100,000-year problem is real and unresolved. The mid-Pleistocene transition is real and not fully explained. The dynamics of glacial terminations are understood in outline but not in detail, and the relationship between the natural Milankovitch system and the human-modified carbon cycle is a genuinely new problem that the historical record cannot fully constrain. We are living in a moment when the most ancient astronomical rhythm of our planet's climate is intersecting with the most rapid and human-driven perturbation to that climate in the geological record. Understanding the rhythm is part of understanding the perturbation. Knowing where we are in the cycle, knowing how the feedbacks work, knowing what the Earth system has done in the past when these mechanisms were operating, is essential context for understanding what the Earth system might do under the novel conditions we are creating. The ice cores that preserve the record of 800,000 years of Milankovitch cycles are not merely historical documents, they are calibration data for the future, the best guide we have to how the Earth system responds to the forcings we are applying. Limited in their applicability to novel conditions, but irreplaceable as a foundation for understanding. And perhaps most importantly, the ice cores are a reminder of perspective. The 100,000-year cycle has been running for at least the past 2.5 million years. It will continue running for millions of years hence. Human civilization occupies a thin sliver of that timeline, one interglacial out of many, 12,000 years out of millions. The decisions made in this century will affect the climate of the next several centuries, and perhaps the next several millennia. They will not affect the long-term astronomical forcing, or the fundamental dynamics of the Earth system on geological timescales. The planet is not fragile on geological timescales. It has survived the Permian extinction, the Chicxulub impact, the snowball Earth glaciations of 650 million years ago. It will survive whatever we do to it. What is fragile on civilizational timescales is the specific configuration of climate conditions within which human civilization developed and on which it depends. The Milankovitch cycles are the context for that configuration. They explain why the Holocene is warm. They explain why it is unusual in the history of the past million years. And they explain why the stability that allowed civilization to develop is not a permanent feature of the planet, but a phase in a cycle that will eventually bring the climate back toward glacial conditions, on its own time scale, in its own time, according to its own astronomical schedule. Understanding the schedule is understanding our place in time, and understanding our place in time is perhaps the beginning of acting wisely within it. Let the ice settle around you gently tonight, not the ice of the glacial maximum, which is too cold and too heavy for comfortable imagination, but the idea of it, the knowledge that 12,000 years ago, the land you are resting in tonight was either under ice or profoundly altered by its presence, that the world your civilization was built in, the stable, warm, relatively predictable world of the Holocene, is itself a phase in a cycle that has been running for much longer than civilization has existed. The stars above you tonight are the same stars that Milankovitch used to calculate the geometry of the Earth's orbit. The gravitational influence of Jupiter and Saturn that slowly changes the shape of the Earth's orbit is still operating, as it always has. The obliquity is slowly decreasing from its current value. The precession is continuing its slow wobble. The ice cores that preserve the record of the cycle are still down there, under the Antarctic plateau, under the Greenland ice sheet. The compressed air bubbles from 100,000 years ago, from 200,000 years ago, from 400,000 years ago, are still there, waiting in the ice, carrying their ancient atmospheric chemistry in perfect preservation. And the cycle itself is still running, slowly, on its own time scale, indifferent to our civilizations and our concerns and our brief, extraordinary presence on its surface. What the cycle tells us is that the Earth is not background. It is not a stage on which human history plays out. It is an actor. It has its own dynamics, its own timescales, its own ways of changing that were operating for billions of years before we arrived, and that will continue for billions of years after we're gone. We exist within those dynamics. We emerged from them. We have now begun to alter them, modestly by geological standards, profoundly by human ones. The 100,000-year heartbeat of the planet is slower than anything human culture can easily imagine, but it is real. It can be heard in the ice cores, it can be measured in the marine sediments, it can be calculated from the astronomical mechanics that Milankovitch derived by hand, and it is, in the deepest sense, the rhythm we were born to, the rhythm that made us what we are. The rhythm that for as long as we inhabit this planet we will always be responding to, whether we choose to understand it or not. Understanding it seems better. Rest now. The eccentricity is doing what it always does. The obliquity is slowly decreasing. The precession is wobbling on its 26,000-year cycle. The Earth is, as always, somewhere in its 100,000-year heartbeat. You are in the warm phase. It will not last forever. But it has lasted long enough for this civilization, this conversation, this specific moment of a species understanding the rhythm it was born to. That is enough. Sleep well.